Good morning all. So today we are going to discuss about the DSB-SC signal. Last class we have solved some numericals regarding to the envelope detection, square law, demodulator, as well as some numericals which is belongs to coherent detection also. And we have seen if there is a variation of modulation index, then what will be the output of envelope detector. Now that is the part up to AM generation, means basic. What are the modulators, what are the demodulators for AM generation. Now in the previous class we have discussed that there are different type of AM signals are available. Okay, so one by one we are going to discuss those AM signal according to their generation as well as to the detection, and we will see what are the which AM signal is more efficient as compared to the other AM signal. Now as the discussion what we have done with respect to envelope detector, which is basically used to detect the AM signal, either it can be a double sideband with carrier, double sideband without carrier or suppressed carrier, or SSB-SC or VSC. So those are the types of AM signal. Now if I will say type of AM signal, so how many types of AM signals are available? As we have discussed in the previous class, there are three basic AM signals are available. One is double sideband suppressed carrier. Okay. One is single sideband suppressed carrier. SC means suppressed carrier. And last one is vestigial sideband with suppressed carrier, VSB-SC. Now this is DSB-SC, SSB-SC and VSB. These are the types of AM signal. But AM is also called as double sideband with carrier component. So these are the three types of AM signal which we are going to discuss for generation as well as detection. As we have done for AM signal, we have generated the AM signal with the help of square law, diode modulator is there. Then if it is a detector is available, the detectors are also, we have seen synchronous detectors are there, envelope detectors are there, then squaring loop detectors are available. So with the help of those things we have reconstructed the modulating signal if AM signal is transmitted. Similarly here there are different types of AM signals are available. With this sort of AM signal, the various demodulators are available through which we can generate the DSB-SC signal, SSB-SC signal as well as vestigial sideband signal. So before entering into this particular part, I will discuss about the type of communication. Because these are the modulation techniques through which communication process can be done. So type of communication, if I will say, that means there are two types of communications are available. One is baseband transmission. Okay, one is baseband transmission and one is carrier communication, or this is baseband communication or transmission you can say, and another one is carrier communication. Okay. Now what is the difference between these two communications? In these two communications the difference is in baseband only we are going to transmit the modulating signal which is of very low frequency, 3 Hz to 300 kilohertz or 3 kilohertz to 300 kilohertz you can only transmit. So if the frequency is less, it will travel to the less amount of distance. Okay, as if it is covering to a short distance, then we prefer for this baseband communication or baseband transmission. So baseband transmission means low frequency communication. Now the low frequency communication example is the telephones. Why? I will tell. This telephone means land phones are there. Okay. So in this land phone, we require less potential, less amount of frequency component to reach to a certain distance. So this is the baseband communication, means only the modulating signal is going to be delivered in the channel. Similarly, the carrier communication means here the modulation takes place. In this case, the modulation takes place. Which type of modulation? Carrier modulation. Now carrier depends upon the nature. If the carrier is in pulse, then it is called pulse modulation. If the carrier is a continuous, then it is called continuous wave modulation. Now this AM comes under this continuous wave modulation. Similarly, angular modulation comes under continuous wave modulation. So these are the certain variation depends upon the type of communication. So basically type of communication are two types. One is baseband transmission and one is carrier transmission. Baseband means only modulating signals we are going to transmit in a particular channel without the modulation. So without the modulation means if I am going to transmit only the modulating signal whose frequency is very small, that means the requirement of the height of antenna will be very high and it is impossible to design. And so that we are preferring this carrier modulation. Here what happens, the lower frequency is converted into the higher frequency and we have seen that relation, the height of the antenna, how it is related to the frequency component. Now height of the antenna is inversely proportional to the frequency component. If frequency is high, height of the antenna is going to be less, which is easy to design. So we prefer this carrier modulation. This carrier modulation comes under your cellular communication. But this baseband transmission comes under your telephones, land telephones. Okay. So these are the two communication parts through which you have to understand the AM modulation. We have already gone through this AM modulation, how it is generated, how it is detected, how many type of detectors are available and what is its procedure, how we can reconstruct the modulating signal and all. Now we will see the type of this AM signal. First, DSB-SC. So first we will understand what is DSB-SC and then we will generate the DSB-SC with the help of certain modulators and then we will detect the DSB-SC with the help of the detector what we have discussed in the last classes. Okay. So first we are going to discuss about DSB-SC. So first is DSB-SC. So DSB-SC itself indicates that double sideband with suppressed carrier. Okay. Now, how we can suppress the effect of carrier? And that it should be a modulator. Now, the word modulation itself indicates that we are changing the characteristics of carrier component with respect to the instantaneous variation of amplitude of a modulating signal. Then only we are saying it is called as a AM generation or amplitude modulated signal. Since we need to identify the double sideband without the presence of carrier, that means, for example, if I will write AM signal general expression, okay, what I will write? I will write carrier AC cos omega C done plus M of t cos omega C. So this is my AM signal. In AM signal, it is also called as double sideband with carrier. Yes, carrier is present and double sidebands are also present. What are the double sideband? One is lower sideband, one is upper sideband. So this component reveals the sideband and this component reveals the presence of carrier. So now when we are using AM, the maximum amount of energy we are losing to transmitting only the carrier, which does not convey any sort of information. That proof also we have seen. And only 33% of the power is used to transmit the information. Okay. So if this component is suppressed, that means 100% efficiency can be done. Okay. If this particular component, if we suppress, that means only the sideband we are going to transmit. If the sideband we are going to transmit means when I will calculate the efficiency, as we have a relation, it is a efficiency means it is a ratio of a sideband divided by the total power into 100. So now if I am going to use the sideband transmission, that means the total transmitted power depends upon sideband. So your efficiency will become as 100. That is the advantage of DSB-SC signal over AM signal. So how we are going to suppress the effect of carrier? Let's see. Okay. So this is the equation for AM signal. We need to suppress this effect of cos omega Cp so that only the sideband is available and the sideband we are going to transmit with the help of a transmitting antenna towards a particular channel. Okay. So for that certain arrangements we need to do so that the DSB-SC signal can be generated. Okay. Now for that the simple logic is, this is my modulating signal. Okay. This is my modulating signal. Now as the carrier is having certain amplitude AC and then cos omega Ct, whatever it is. So let us consider this is the carrier component whose frequency is very high as compared to the modulating signal. So this is my C of T. Okay, and this is the time period. This is 0. This is modulating signal. Now if I need to modulate the carrier with respect to the modulating signal. Now here what happens, when I am doing the AM modulation, I am getting an envelope. Okay, getting an envelope. In that envelope it indicates that the amplitude of carrier is varied according to the amplitude of modulating signal. So we are adding amplitude of carrier plus modulating signal whole into cos omega Ct. But if directly this carrier is varied according to the amplitude of modulating signal, then the DSB-SC signal can be generated. So here you can see, here I am discussing about time domain. Then we will discuss about the frequency domain later on. For the understanding purpose, first I am discussing the time domain representation. So if the DSB-SC signal need to be generated, DSB-SC of T. So that means the amplitude of carrier must follow the path of modulating signal. So my modulating signal will look like this. Okay. And these are the sidebands. Okay, so this is the sideband. So first, the modulating signal what I am identifying is the modulated signal. And here what happens, at the zero crossing, the phase inversion of a carrier takes place. That is the difference. Okay. So this is my DSB-SC signal. Now how I will identify the DSB-SC signal? Here you can see for a positive half the amplitude of a carrier follows the path of modulating signal. Yes, it is following for positive and negative. Similarly, for a negative half the carrier goes down and again it forms as a double sideband. So this is called as a DSB-SC signal. How to identify? You have to check that at a zero crossing of the modulating signal, Okay, at the zero crossing of the modulating signal, your carrier phase should change from one phase to the other phase. So here it is changing. Suppose here it is moving up, then it is moving into the another phase. So this is the first one. Okay, so with the help of this representation, we can analyze with mathematical expressions. Okay, how we can represent this DSB-SC signal? Let us see. For this, that means my resultant output is m of t cos omega ct. So this is the DSB-SC signal. Okay. Now this is the DSB-SC signal. I need to generate this particular part. For this, what I will do, I will use a balance modulator, or it is called as a product modulator. What we have discussed in our AM signal, there is a product modulator is there. But here it is a balanced modulator. The balanced modulator later on we will discuss in an explanatory form. For the time being, only we will discuss how these expressions we are extracting. Then we can understand the principle of this balanced modulator. The output of balanced modulator suppresses the effect of carrier and only the sideband he is providing. Okay. So this is my balanced modulator. But when I am generating AM signal, I am using the product modulator. This is the difference. So this is the balanced modulator. The one side message signal is provided, and here we are providing the carrier component cos omega ct. Okay, and the output what we are getting, it is called m of t into cos omega ct. So this is the DSB-SC signal we are receiving. So how to get this DSB-SC signal? It is done with the help of our balanced modulator. There are two different modulators are there that we will discuss for generation of DSB-SC signal. First one is balanced modulator, second one is the ring modulator. Okay, so depend upon those two modulators, we are generating the DSB-SC signal with suppressed carrier. Means effect of carrier is not there. Here you can see only the sideband is available. That we can identify with the help of Fourier analysis. We will see all those things. So here m of t cos omega ct will become as a sideband, and there is presence of carrier is suppressed. So here we are getting the double sideband suppressed carrier. So how we can analyze this one mathematically? So mathematical analysis. So first we have to consider the modulating signal. Let us consider it is Vn cos omega nt. Then again you have to consider the carrier is cos omega ct. In some of the book they may consider the amplitude of carrier as AC. In some of the book they may not consider the effect of AC. Anyway, the effect of carrier is going to be suppressed if they include the amplitude or it may not include the amplitude. Doesn't matter. Okay. So here I am not considering the amplitude. Here I am considering the amplitude of carrier is 1, which is going to be changed with respect to the m of t. So now the output of balanced modulator, we will get the DSB-SC signal. So S suffix DSB-SC of t is equals to m of t into c of t. So if S suffix DSB-SC of t is equals to m of t cos omega ct. Okay, in place of c of t I have substituted cos omega ct. Now I need to simplify this. So it is Vm cos omega mt into cos omega ct. If I will expand this, I will get, it is in a form of cos A cos B. So it is Vm by 2 cos of omega c minus omega m of t plus cos of omega c plus omega m of t. Okay, so this is the two side bands are available. Here you can see omega c minus omega m is indicating the lower side band and omega c plus omega m indicates the upper side band. Done. So depend upon this relation, we can see that DSB-SC is only consist of side band and the presence of carrier was suppressed. Okay. Now this is the mathematical expression. Now same expression I can write with respect to the frequency translation. So frequency translation also we have to form. So what I will do, I will use the Fourier analysis. Then only the frequency spectrum I can plot. So Fourier analysis. Okay. Now Fourier analysis means, as we have written, C of t is equals to cos omega ct. Now this cos omega ct I can write half of e to the power minus j omega ct plus e to the power j omega ct. Done. Now depend upon this, if I will find out the Fourier transform of this equation, then I will get, here it is exponential and amplitude is 1, that means I can represent this component in terms of del. So what I will write, it is half of del of, it is a frequency shifting f minus fc plus del of f plus fc. So it is a frequency shifting property for fc of f. Now what is the Fourier transform relation? Fourier transform relation is c of f minus infinite to infinite c of t e to the power minus j omega t into dt. So this j omega reveals f and here it is omega c. If I will multiply these two component will come 1 f minus fc and then f plus fc. So this is the frequency component for your carrier. Done. So we have obtained this relation with the help of this particular Fourier transform. Now we have to achieve this modulated signal. So here m of t into c of t. Okay. Now in signal system you people have gone through the Fourier transform of a multiplication property, it will become as a convolution. Okay. So here I can write s of f is equals to m of f convolution with c of f. So this is the modulated signal. Done. Now this m of f is what? M of f is our modulating signal. So if m of f is multiplied with this component, or here you can take it is a convolutional multiplication whose Fourier transform is only simply a multiplication with the frequency shifting, then it is multiplication and here it is a convolution, then what will be my s of f? So s of f we will see so s of f, that is DSB-SC signal, m of f into this. So in place of del it will become as m. So it is half of m of f minus fc plus m of f plus fc. Okay, and that the modulating signal is having certain frequency fm. So here I will write, in place of f plus fc I will write fc minus fm and fc plus fm. So that means this is my side bands. Okay, so this is the side band what we are available at the Fourier this. Now this sideband we need to plot in this spectrum. So whatever the relations we are getting, it is with respect to DSB-SC. Okay. So here we have got two sideband. One is lower sideband, one is upper sideband, and then it is called as our double sideband suppressed carrier. Now here we have discussed about the time domain. This is the time domain. Now same thing, if I will write in terms of frequency domain, in frequency domain. So first one we have considered, this is my modulating signal. So modulating signal, if I will take Fourier transform, the representation I will get, this is FM and this is the replica of FM. So this is M of F. Okay, and what is the amplitude? Amplitude is Vm, but the amplitude will become as a Vm by 2, as we have seen y is 2. So here I am not discussing about the amplitude. Here I will write M of 0, because at 0 what will be the amplitude? It is the same for your modulating signal. Then next one is carrier. So carrier, how we have represented? The carrier is C of F. C of F is having 1 at plus Fc, 1 at minus Fc. So 1 is at Fc and one component is available, replica is minus Fc. So this is my C of F. Okay. Now after modulation, what happens? After modulation, only we are considering the sidebands, no carrier component, it is suppression. Okay. So this is the DSB-SC signal. So DSB-SC signal, here this is the Fc dotted line, means suppressed minus Fc, and here two sidebands are available. Okay, that is Fc plus Fm, and another one is Fc minus Fm. Okay, so here it is minus Fc plus Fm, here it is minus Fc minus Fm. So this is the sidebands are available with suppressed carriers, and this is called as my S of F. Here I am not discussing about the amplitude, I am discussing only the representation of frequency component. So these are the two sidebands available for DSB-SC signal. Now in this figure, again we can consider what is the bandwidth. So bandwidth is equals to higher frequency minus lower frequency. This is the higher frequency, this is the lower frequency. If you subtract it, you will get 2 FM. That means what it indicates? The bandwidth of AM and bandwidth of DSB-SC signal both are same. So this is the general representation for the DSB-SC signal. One is for time domain and one is for frequency domain. So this is the reflection of a DSB-SC signal, what we are going to discuss now with respect to single tone and with respect to multi-tone. In that we will assign the potentials. In that we will assign certain power, so that power relation can also be formed and efficiency can also be calculated. Okay. So up to this, it must be clear for you. Next I will discuss how to calculate power. Then we will go for single tone and multi-tone. So as we have calculated power for AM signal, similarly we can calculate for DSB-SC signal. So the total power we can write PT is equals to PC plus the sideband. So this is the total power for AM signal, for amplitude modulated signal. But since we are discussing about DSB-SC signal, in DSB-SC signal the effect of carrier is suppressed and only the sidebands are available. So total power transmitted for DSB-SC is equals to sideband power. Now what is this sideband power? The sideband power is nothing but power available at lower sideband plus power available at upper sideband. So here you can see that available of power in lower sideband and upper sideband, we have seen that both powers are equal. Okay. Now how much we have calculated for them? We have calculated Vm square divided by 8R. This relation is related to the AM, how we have calculated. Directly I am writing this one. Similarly, the power available at upper sideband is Vm square by 8R. Now, these two when I will add, we will get Vm square divided by 4R. So this is the total sideband power. Okay. I am not deriving this relation once again because it is already discussed. Directly I am writing this value. So sideband power is Vm square by 4. Here the total power is delivered is only the sideband. There is no presence of carrier. Effect of carrier is suppressed. Okay. We can't say there is no presence of carrier. Effect of carrier is suppressed. Only sideband we are transmitting. If we will say that total carrier is removed, means there is no possibility of modulation. Since DSB-SC is a modulated wave, that means carrier is there, but effect of carrier is suppressed. Okay, only the sidebands are available. So this is the sideband power. So now, if I am calculating the efficiency of transmission, efficiency of transmission states that it is a ratio of sideband power by transmitted power into 100. Okay. Now if it is DSB-SC, efficiency is sideband power and transmitted power both are same. So here I will write it is 100% transmitted efficiency is done, which is the advantage over amplitude modulation. In amplitude modulation, 66% of total power we are wasting to transmit the carrier signal, which does not convey any sort of information. But in DSB-SC, if we suppress the effect of carrier and transmit the sideband power, that means the total efficiency will raise up to 100%. Okay, it is only theoretical calculation, but practically 100% efficiency is not possible. 98%, even 99.9%, but still there must be a tolerance is available in practical case. It is only for ideal case what I am discussing. Okay, so depend upon this, the total power is transmitted and efficiency is also calculated. Okay, now we will see with respect to single pole, and we will represent those signal with certain mathematical equations as well as frequency spectrum. One minute. Okay. So first we will discuss about single tone modulated signal. For DSB-SC signal. Now, as we have discussed in this class, that we have considered only one frequency, so it can be used for our single tone signal. Let us consider or mathematical analysis directly we will discuss. Mathematical analysis. M of t is equals to V1 cos omega 1. Okay. So only one modulating frequency is available in our modulating signal with amplitude V1. And carrier is cos omega c. Let us consider AC for this case. You can consider AC, you may not consider AC, no problem. Output will be your DSB-SC signal, you will see. Now when these two signals are passed through balanced modulator, we will get DSB-SC signal. Okay, so this is M of t. Here it is AC cos omega ct generated by local oscillator. Here you can represent this is local oscillator, and DSB-SC signal is generated. That is M of t into AC into cos omega ct. So this is my relation. I need to expand this relation so that I will get these spectrums. So S suffix DSB-SC of t, in place of M of t, I will substitute V1 into AC into cos omega mt into cos omega c. So here omega m, either you can consider omega m or omega 1. So let us consider it is omega 1. Done. Now you need to expand this. So V1 AC is the amplitude divided by 2, and this component you can write cos of omega c minus omega 1t plus cos of omega c plus omega 1t. So this indicates that this is your lower sideband and this is your upper sideband, but the presence of carrier is suppressed. There is no effect of carrier. Effect of carrier will be there, but maximum part we have suppressed. So here this is the equation for our DSB-SC signal. Okay, so this is the DSB-SC signal. Now this DSB-SC signal need to be represented in a frequency spectrum. Okay, so I will draw the frequency spectrum. Frequency spectrum for DSB-SC signal. So first identify the position of carrier frequency. This is your Fc and this is your minus Fc. Then this is your S suffix of F. Now S suffix of F is the Fourier transform value of S of t, means DSB-SC signal, in which the upper sideband is available as well as lower sideband is available. Upper sideband is available Fc plus F1, lower sideband is available Fc minus F1. Like this you can represent this. Now the term comes, what is the amplitude of it? Now here you can see V1 AC by 2 is the amplitude. But it is a power relation. So power relation means divided by 4 it will come. Half of the power is available here, half of the power is available here. So that the total will become as a V1 AC by 2. So here V1 AC divided divided by 4, V1 AC divided by 4. If I will add these two potential, I will get V1 AC by 2, which is the total sideband power. Okay. Similarly, for the negative half or the reflection part, you can represent the same amplitude, but the frequency is minus Fc plus F1 and minus Fc minus F1. Okay. And what is the amplitude? Again it is V1 AC divided by 4, V1 AC divided by 4. So this is the amplitude of the sideband. And what is the amplitude of carrier? There is no presence of carrier, so we not to consider. So this is the sideband. So if this is the sideband, so what will be my bandwidth? So bandwidth is higher frequency, this is the lower frequency, and bandwidth states that Fh minus Fl. Fh is how much? Fc plus F1 minus of Fc minus F1. So that means it is twice F1. So this is the bandwidth of DSB-SC signal. Done? So this is the bandwidth of DSB-SC signal for frequency spectrum for a DSB-SC generated signal. Okay. So here only we have used only one frequency for a modulating signal. So it is called as our single tone modulated signal. Now we have to calculate the power for this. So then we will calculate efficiency for this. So individually we have to calculate. So step by step we will see. So first the power calculation. Then we will calculate the efficiency. So power calculation. So total transmitted power is equals to carrier power plus sideband power. This is for AM. Now power transmitted with respect to DSB-SC signal. The power of carrier is suppressed and we are transmitting only the sideband. Now what is the sideband power? Sideband power is power available at lower sideband plus power available at upper sideband. Okay. Now how to calculate lower sideband power? Lower sideband power, since this is the amplitude, it will become AC square by 2R. So it is V1 AC divided by 2 square divided by 2R. This is the power relation. So if I will solve this, I will get V1 square AC square divided by 8R, which is equal to upper sideband. Okay, because the lower sideband and upper sideband power is equal, you need to add those two power. So what I will do, I will write sideband power is equals to upper sideband power plus lower sideband power, which is equals to V1 square AC square divided by 8R plus V1 square AC square divided by 8R. If you add these two, you will get V1 square AC square divided by 4R. So this is the sideband power or the transmitted power for your AM, for your DSB-SC signal. DSB-SC signal. So this is the relation. Okay. So this is the relation for what? It is the power relation. Sideband power must be equal to transmitted power. And next we will calculate for the efficiency. So efficiency calculation is easy for this. What is the relation? That also we will see. So efficiency, or it is called as transmission efficiency. Okay. So transmission efficiency states that the ratio of sideband power plus total transmitted power. Now here for a single tone we have seen it is V1 square AC square divided by 4R is the sideband power. But in DSB-SC what happens? Transmitted power is same as this sideband power. So I will write here V1 square AC square divided by 4R, so into 100. So this component cancel out, we will get 100%. So the DSB-SC transmission efficiency is 100%. Okay, simple. Now next we will discuss about the multi-tone. One more important thing, here we are not discussing about modulation index because here the effect of carrier is suppressed. So if the effect of carrier is suppressed, what will be your modulation index? Mod of M of T divided by AC. So if AC is there and M of T if it is equal, maximum is critical modulation is possible. Okay, because in the DSB-SC we are neglecting the effect of carrier, so the modulation index maximum value is 1. If it is greater than 1, DSB-SC signal again lose the information. We cannot reconstruct the original message signal. Okay. So next we will discuss about the multi-tone signal. So this is the multi-tone signal. Now as the word called multi-tone means your modulating signal must consist of more than one number of frequency with same amplitude or different amplitude. Okay. So let us consider, first I will start with this mathematical analysis, then we will represent the frequency spectrum, and then we will calculate the total transmitted power and efficiency. Okay. So first M of T is equal to V1 cos omega 1 t plus V2 cos omega 2. And the consideration is your omega 2 is greater than omega 1 and V2 is greater than V1. This is the consideration. Okay. Now carrier, let us consider it is AC cos omega C. You may consider AC, you may not consider AC. It depends upon you. Okay. Next, this is the balance modulator. This is balanced modulator, in which carrier is provided AC cos omega C, and here modulating signal is provided, and here you will get the DSB-SC signal. Done, and this is the transmitting antenna. It will transmit the DSB-SC signal. Now, as per the block diagram, I can write S DSB-SC of t, time domain analysis what we are doing, m of t into cos omega ct into AC. Directly I am writing in place of c of t, AC cos omega ct. In place of m of t, you can write v1 cos omega 1t plus v2 cos omega 2t whole into AC cos omega ct. So this is the relation we will get. Now you need to expand it. You will get two upper segment and two lower segment signal. So first V1 AC divided by this. First I will expand this component with this. We will get cos omega c minus omega 1t plus cos omega c plus omega 1t plus again with respect to the second frequency component. So it is V2 AC divided by 2 cos omega c minus omega 2t plus cos omega c plus omega 2t. So this is the second frequency component. So what is this? This is the lower sideband 1. What is this? This is upper sideband 1. Now what is this? It is lower sideband for second modulating frequency, and this is the second upper sideband frequency. Done? And these are the two amplitudes are available which need to be distributed among the spectrums. Okay. Now we need to represent this in terms of frequency spectrum. You have to represent this. So frequency spectrum for this I am discussing only about the right hand side. You can plot same thing for left hand side also, or I will represent for both the things. Let me represent for both the things. It will easy to understand. So it is S suffix DSB-SC of F. So first what we have to do? First we have to identify the position of carrier frequency. Okay. That is the center frequency. Dotted line means absence of carrier. Now first it is FC plus F1. This is the lower sideband FC minus F1. As we have considered that second frequency F2 is greater than F1, so that means here I can represent FC plus F2, and here I will represent FC minus F2. Now why I have represented this amplitudes a little bit low, a little bit high? Because here we have considered that second modulating frequency is having the higher amplitude with respect to the first one. So here the amplitude we will decide how much it is later on. First we have identified the points. Similarly, the amplitude for the first frequency, this is minus Fc plus F1, this is minus Fc minus F1, and this is minus Fc plus F2, and here minus Fc minus F2. So this is the LSB 1, this is LSB 2, this is USB 1, this is USB 2. Similarly, this is LSB 2, this is LSB 1, this is USB 1, this is USB 2. So this is the frequency translation of this particular equation. Now we need to assign the amplitude. Okay, so how we will assign the amplitude or the power content in the particular spectral component? Let's see. So this is S of F, and the presence of carrier is this one, Fc. Here also it is minus Fc. This is the first sidebands for omega 1t, and these are the upper sideband and lower sideband for omega 2t. So here I will write Fc plus F2 as I have written here, then Fc plus F1 as I have written here. This is the carrier frequency, Fc minus F1 and Fc minus F2. This is 0. Done. Then again just the reflection. So this is first, this is the second, and this one. So this is minus Fc plus F2, this is minus Ft plus F1, this is minus Ft minus F1 minus Fc minus F2. So as per the figure I have represented. Now I need to assign the amplitude for this. So this is S of F. Now here, as you can see, it is V1 AC by 2. It is the total power available in the sideband with respect to the first component. So total sideband means it need to be divided by the lower sideband and upper sideband. How I can represent? So first sideband is V1 AC by 2 is available. Now LSB, here I am discussing only the potential. Okay, so here I am representing the potential in the sideband. So potentials available in the lower sideband, potential available in the upper sideband. So it is sideband potential divided by 2. So how much it is? V1 AC divided by 4. So what I will write? V1 AC divided by 4. V1 AC divided by 4. So that if you add these two, you will get V1 AC by 2. Done? Similarly, the same principle will be followed by the second modulating frequency, that is V2 AC divided by 4, V2 AC divided by 4. Same thing you should reflect in left hand side. Here it is V2 AC divided by 4. This is V1 AC divided by 4. V1 AC divided by 4. This is V2 AC divided by 4. So this is the amplitude available in the frequency spectrum for multitone signal. Okay. Now we will calculate the power availability in this particular signal, and then we will calculate the efficiency. So power calculation. So power calculation. So total power for DSB-SC must be equal to the sidebands. Okay. So first of all I need to calculate the sideband. So power available in sideband means the power available in the sideband with respect to first, power available in the sideband with respect to second. Done. Then here PLSP 1, PUSP 1, PLSP 2, PUSP 2. Okay. Now this power already we have calculated, only we need to change in place of V1, V2. So available in the power in lower sideband, I can write V V1 square AC square divided by theta. Upper segment it is V1 square AC square divided by theta. For second, in place of V1 substitute V2 square AC square divided by theta plus V2 square AC square divided by theta. So this is the total power available in the sidelines. Now if I will add all these things, how much we should get? Let's see. So sidewind power, if I will add these two components, I will get V1 square AC square divided by 4R plus add these two components V2 square AC square divided by 4R. So you need to add these two, you will get AC square divided by 4R whole into V1 square plus V2 square. So this is the total sidewind power, and transmitted power is same as sidewind power. So your efficiency again it will become 100%. This indicates what? Either you go for multi-tone, either you go for single tone, your efficiency will become as 100% of transmission. This is the principle of DSB-SC signal. Next class we will discuss about the generation of DSB-SC signal and how many type of modulators are available to generate the DSB-SC signal, that we will discuss. Okay. For the time being, we will end up this session. Thank you all.